Now let's try method 2 of determining the acceleration of a rolling sphere with no slipping. Method 2 is analyzing the torque about the center of mass of the sphere. Now the center of mass of the sphere is right about there. Let's go ahead and draw that rotational axis symbol right there. That is the rotational axis we're going to analyze this about, which makes sense, intuitively. It's spinning about that axis. So let's go ahead and figure out what all the forces are. So we're going to have to draw all the forces, and very important when you're using Newton's laws, which is what we're about to do, you've got to draw the forces acting at the point of force application. So this is something that I wasn't necessarily required before, but now is essential. The tail of the arrow must be at the point of force application without any exception. So what are the forces that are acting here? Let's go ahead and draw them all in. So the first force we got is the force of gravity. Okay, I'm also going to get rid of this line here so it doesn't get in the way of our free body diagram. And we'll just we'll get rid of this too for the moment. We're not even going to need that. Let's draw in the force of gravity. This is mass m. This is going to be mg. Cool, there's one force. And notice I have the tail of it at the center of mass. Gravity always acts as if it's always, the point of force application is at the center of mass. What other forces are acting on this? Well, I've got the normal force. Let's use red for the normal force. Here's the normal force. The normal force is happening right there. That is the normal force right there. N is the symbol I'll use for that. What other forces are acting? Now this is rolling without slipping, but that doesn't mean that there's no friction. In fact, there is friction. I'm going to use the color green for the force of friction, and that's acting right here. But it's not slipping, so that is the force of static friction, F sub S. That's how I'll indicate that. Are there any other forces acting on this thing? Got gravity, got the force of static friction, and the normal force. No, there are not. That's all there is. So now what I got to do is we're going to analyze this in terms of Newton's laws, both translationally and rotationally. We could split into X, Y, and rotational. For this, just I'm going to save some time, it is true that in the Y direction, the normal force will be equal to mg cosine theta. And so we've done that many, many times. It's just a ramp. There's nothing inclined plane, nothing special about it. So I'm going to skip the Y analysis. We're just going to stick with the translational, which is going to be in the X direction. And then we're going to also have the rotational motion. So it's kind of a similar thing where you split into X and Y, but we're going to split into translational and rotational. Now, let's see what we can do about the translational motion. What I'm going to do is I'm going to only look at the X component. So really all I have to look at is the X component of gravity. So I'm going to draw that in blue, just this X component. The X component of the force of gravity is just mg sine theta like before. Now, of course, on the AP exam, they don't want you to draw components. You'd have to draw components on a separate sheet or a separate diagram. So for now, let's pretend we've done that. I don't mind you, for problems in my class, just drawing it right on there. But keep in mind, the only real force is gravity, mg sine theta and mg cosine theta. They're not separate forces. They're just components of gravity. But this is the only part that's acting in the X direction. So let's go ahead and just write our translational motion equation here. Net force X equals max. And what are the forces in the X direction? Well, there's mg sine theta. We'll keep the blue for that. Mg sine theta, that's positive or negative? Well, positive. And minus Fs, the force of static friction. We don't know what the force of static friction is. Even if we knew mu, we wouldn't know the force of static friction because it depends. We have to figure that out. You could only use the static frictional equation if you wanted the maximum force of static friction that it could ever exert. We don't necessarily want that, so we can't use the mu times the normal force equation for this. here's what we do know, that it's going to be equal to max. Are there any other forces in the x direction? No, that's it. Well, that doesn't finish this problem for us. We got two unknowns, ax and the force of static friction. So what we have to do is go to the rotational aspect. Let's go ahead and look at that. Now, for rotation, you got to pick an axis of rotation. We have already picked, for this method, about the center of mass of the sphere. So we're going to analyze torques about there. So let's figure out which of these forces actually will exert a torque about the center of mass. Well, here's where our lever arm and concepts of what R is really come in handy. Now let's recall that R for torques is the displacement between the axis of rotation and what? The point of force application. So let's look at each one of these forces acting right here and see if it exerts a torque. So mg, where's the point of force application? Boom, the center of mass. Always the weight, or the force of gravity, same thing, will be acting at the center of mass. What is the distance between the axis of rotation and the point of force application? Hint, they're both right there for gravity. So what is that? Distance or displacement r? It's 0. So gravity exerts no torque about the center of mass. So I'm just going to say no torque for gravity. No tau for gravity. Won't exert any torque about that axis. How about, and you could also, by the way, look at mg sine theta. That's the same, it's just a component of the force. You could pretend that it's a separate force. It's acting right there too. So no torque for that either. What about the force of static friction? Well, yes, that's going to exert a torque right here. So we've got the force of static friction. It's pulling right there. It's acting at that point. So that will, in fact, exert a torque. What will that torque be? Well, let's just call it the torque due for right now. And we got to decide which way we want to call positive. You should always call the angular acceleration, which in this case is going to be this way. There is alpha. You should always call that positive in the same direction that acceleration is positive. In other words, alpha rolling around clockwise will cause a positive acceleration down the hill. So that clockwise in this situation is going to be positive. So we are going to say, well, let's go ahead and write our general equation. For torques, we have the net torque, and I'm going to do it about this center of mass. About the center of mass, because it'll be different about different axes, is going to be I about, guess which rotational axis. If you said center of mass, you'd be right, times alpha, the rotational acceleration. So, but now I gotta actually get more specific, and what we were just talking about is that the force of static friction is going to exert a torque. Let's come back to that in a minute. I want to just ask, is the normal force going to exert a torque? Well, this is where the lever arm comes in incredibly handy. What is, let's go ahead and draw the line of action of the normal force. That goes all the way through right there. What is the shortest distance between the line of action of this normal force and the axis of rotation? Well, it goes right through the axis of rotation. So the lever arm is 0. So we've got the normal force also exerts no torque. No torque due to the normal force. But as we said before, the force of static friction will exert a torque. In fact, it's the only force that will exert a torque about that axis. So what is the torque that it exerts? Well, in general, the torque, again, we got to calculate this separately, is going to be R cross F. Let's go ahead and put that right here. R cross F is going to be the torque. Let's be more specific. What R and what F? Look right here. This is the radius of the sphere. That's Fs. So this is going to be the radius of the sphere, R of the sphere, times the force of static friction, which we don't know what it is, put that in green, times the force of static friction, times the sine of the angle between them. Now let's look at the sine of the angle between them, sine of theta. What is the angle between R and F? We've got to put them tail to tail to figure that out. But here's R, here's F. If you put them tail to tail, it's still going to be 90 degrees. So that is going to be 90 degrees, and that just goes away. That's 1. So R times Fs equals, I about the center of mass was already given to us. That is 2/5 mr squared. For a sphere, that would have to be given to you times alpha. So I'm just going to neaten this up a little bit and get our other equation. R times Fs equals 2/5 mr squared times alpha. Now I've got this equation right here, and I've got this equation right here. Now, there is too many variables to solve this, but the good news is that we can interrelate translational and rotational motion. So I'm going to put that in the middle here, because really, this will interrelate the two. In fact, AX will equal, and that's going to be the same as the tangential acceleration, AX will equal R alpha. So this is going to help us a lot, because this gives us the third equation that we need to solve, because otherwise we've got 3 unknowns. We've got AX is unknown, the force static friction is unknown, and also alpha is unknown, but this will actually give us 2 equations. So when we use that, what we're going to end up with is these 2 equations, mg sine theta minus Fs equals max, and we're going to end up with, I'm going to use this right here. And R times Fs equals 2/5 mr squared. I'm going to substitute for alpha, and this is something you almost do every single time. Instead of alpha here, I'm going to put in AX over R. So that gets rid of one of those unknown variables, and then we can solve this simultaneously. Now, a couple things we might want to do before we do that is just simplify one more time. Notice that this R cancels that R, okay? And then we have these 2 R's, which also cancel. Hey, cool. Notice that we're left with Fs, the force of static friction, is 2/5 max. So I'm just going to substitute that in right here. mg sine theta minus this whole thing, 2/5 ax. Fs is just going to be 2/5 rather times max, I should say. That'll equal max. And when you solve this for a, notice again we see that m doesn't matter. When you solve this for ax, you again get 5/7 g sine theta. Done. So you got to decide, do you like that better than kinetic energy? Well, we actually still have one more choice. And interestingly, although this seems like anti-intuitive, this may be the next one may be the best choice. I believe it certainly is, and I think it's the easiest way to do it, although it's not as intuitive. So let's go ahead and try method 3.